Okay, so in this example, we want to do something a bit more interesting instead of just letting stuff fall down. And that is, we want to use this ball here to fly against the wall. And unfortunately, this wall will not be destroyed yet because this is a pretty silly wall. It's just a box with a wall texture on it. But we will look at this later in the fracturing section. It's just a bit too complicated for now. We want to talk about a couple of things first. And that is velocity and mass, which we already talked about in Vellum and which play a big role in RBDs as well. So first of all, how do we set this up? Let's start with a wall and we just turn this into an active object. It should react to the simulation. So let's just put it into an RBD bullet solver. And what we should see now, if we rewind this and I start at 1001 because of the pre-roll potentially. So if I press start, it falls down because what I forgot is to activate the ground plane. And now it stands still. Awesome. Now the bigger question is, what do I do with my sphere here? Now, since I know that I want this wall to collide with the sphere, what I could do is I could either put it here into my collision geometry, which is the fourth input. But then the problem is if I press start, then nothing happens because my ball, just doesn't move by itself. Currently, it's just a static collision object. So we could actually animate this sphere to move from A to B. And this is a technique that makes a lot of sense, and we will look at this later on. But let's say we wanted the sphere to react to the wall. Then this is actually not a collision object or a static object, but becomes an active object as well, because we want it to slow down by the wall. In other words, it will be influenced by the simulation as well. So that means we have to actually merge it in with the other active object, our wall. And then for now, if we press start, it falls down. What we need now is simply to move the sphere in one direction. And we already learned in Vellum how to do this. And it's the same here actually. We can, for example, with a point wrangle, just give every single point of my sphere here a start velocity. And you can't see it again because my head is in the way, but the direction would be negative x. So let's give it a bit of oomph, so maybe minus 15 and then a 0, 0, so that it will move into the negative x direction. And if I run this now, there it is. And as you can see, it's pretty simple. Just like with Vellum, we just set a velocity attribute and then our object will move. Another thing we've already seen actually is the next concept, and that is mass. Now, as you can see, when when the two collide, they kind of react in the same strength, so to say. And we can actually change the behavior simply by making our sphere a bit smaller. And remember, in Vellum, we talked about this. This is because the mass will be calculated automatically. And if I run this now, you can see, there's way less energy in our sphere because it's much smaller. This makes a lot of sense and is very logical. But what if I want this sphere to actually react to the wall? And then we can change the mass. And just like we've seen in Vellum, we have two options. We can do this independent of the volume or dependent on the volume. And the way I want to start showing this to you is actually setting it directly as an absolute number. So let's make the sphere a bit bigger again. And to make this work, we have to set a new attribute that we've already seen. It's called mass. Let's do this with a point wrangle, for example. Let's call this mass. And let's set this mass to 100, let's say. What's important here is that you don't have to necessarily see this number as an absolute number like kilograms or something. This is just a number that represents the relationship between the two objects. So you can make the wall 100 and the sphere 10, and then the difference is tenfold. But if you set the sphere to 1 and the wall to 10, then it's also tenfold. So it's just about the relationship. It's not about the absolute number. Now, when you set attributes like mass, you can do it like we did here. We just created the geometry and the wall, and we set the attributes directly. And technically, we set them on every single point of our geometry. There's nothing wrong with that. But remember, since in the RBD bullet solver, objects will be packed anyway, what I would recommend whenever you set attributes to pack your geometry beforehand. And we can do this, as we know, with an assemble, for example, because this has the advantage of not only packing our geometry, but also giving it a name attribute, which will play a role later on. So let's call this maybe projectile or something. And then we copy this example for our wall as well and call this wall. And then we have everything set up correctly. And if we run this now, unfortunately, as you can see, we lost our material, which is typical when you pack something, which is a shame really, but that's the way it is. And if we run this now, you can see nothing really has changed with our mass attribute. And that is because we first have to tell the RBD bullet solver to actually use that mass attribute. And we can do this by adding it to this parameter here, override attributes from SOP. And here we can put in any attribute that we want to override that is actually happening inside of our bullet solver. Now, why do we have to add this here, the mass, and the velocity we didn't have to add? That is because the mass is calculated automatically, as we talked about, based on the scale. And we will talk about this in the next video a bit more, because you don't have to use the mass. You can also keep using the system by using density, and then it will, calculate it based on the volume. But I prefer to work actually with mass, because in my experience, this is easier to work with by just overwriting the absolute number directly. But this is the reason why you have to add it here in this list, because otherwise it will be calculated automatically by the system. So if I run this now, something interesting happens, and that is that the sphere where we set the mass to 100 all of a sudden doesn't move the wall anymore. And the reason for that is simply that we forgot to set the mass for the wall. We only set the mass for the sphere, and that means when we merge the two together, when you look here down at our packed geometry, of course automatically our wall will get a mass of 0. And this is something to be careful of. Whenever you give something a mass of 0, you basically turn it off. So let's make sure we also give our wall a mass, and let's say we want to make it much weaker than the sphere, so we set the mass to 1. And now we have a proper mass which is not 0 for both objects. And if we run this now, you can see that now the sphere is basically so much stronger that it will just, kick the wall away as if it was nothing. We've seen that before in the vellum simulation. And here again, what happens here is that when they collide, the mass will basically define who wins or how the energy is distributed. So if we would, for example, tip it in the favor of the wall by maybe giving the wall a mass of 1,000 and maybe the sphere just of 10, and now you can see, the wall is reacting a little bit, but since the sphere is so much weaker than the wall, the reaction is way less. And with this, you can control the behavior of your simulation more specifically when they collide. And let's quickly unpack this whole thing after the simulation so that we have our shader back. So this is how you set the start velocity and the mass of an object in the RBD solver. I would recommend to pack your objects before you do that, and then it's just simply setting the velocity and the mass attribute, which you have to be careful to add to this override attributes from SOP list so that you can actually override it. Otherwise, it will take the volume into account and calculate the mass itself. And this is something we will talk about in the next video a bit more. So for now, I hope this is helpful. Thanks very much and see you later. Cheers.